The goal of Lesson 8 is to understand the big ideas about slope and y-intercept, as well as linear and nonlinear functions. So in today's lesson, all of the notes are filled in for you, and I encourage you to pause the video and just fill them in, and then just listen as we go through and really try to make sense of the big ideas here, as you'll be able to apply them much easier going forward. Okay. The first big topic we're going to talk about is linear functions versus nonlinear. So in question 1 here, it says all linear functions have x with an exponent of 1. And if you just take a look at this equation, y equals 1/2 x minus 3, you don't see any exponents like you do with here and here. And that's because when you don't see exponents, there is a hidden exponent of 1. Much similar to if you see a lonely variable, there's a 1 in front. When you don't see an exponent, there's a hidden 1. So when you look at equations like y equals 1/2 x minus 3, these make linear graphs. When you graph them, they'll make straight lines on the graph. Now as we change the exponent in example 2, we start with the function y equals x squared, or y equals x to the power of 2. And when you notice, when we graph this using a graphing calculator or some graphing tool, we see that there's a U-shaped graph going on. Well, we call this in mathematics a parabola. The function is in the shape of a parabola, and this is partly because when a negative number is taken to the second power, negative times negative, it becomes positive. So you'll see the graph never really goes below the x-axis because these are all negative numbers. Later on in math, you're going to name this a quadratic, which is in high school. Okay. So again, key differences here: you don't see exponents, we know it's linear. If you see an x squared, you know it's nonlinear. You don't need to know this name, but as moving forward it will be helpful. Part B says, well, what if we change the exponent to a 3? Y equals x to the power of 3. Or what we know as math, y equals x cubed. Then the graph starts to get like a snake, which we call this shape a snake. Partly because if you take negative numbers times a negative, they stay negative. And if you take positive numbers, positive times positive times positive, it's going to stay positive. This is known as a cubic function. But this year, all you need to know is it's nonlinear. It's not a straight line. Lastly, in number 3 here, we can do what you learned last year as an absolute value function. So if we used a graphing calculator to graph y equals absolute value of x, you notice the function is in the shape of a V. And these actually go on. This is known as the absolute value function, which is also nonlinear. It's not one straight line. You might notice that there are 2 straight lines, and this is partly because the exponent is still 1, just like a linear function, but because it's not one straight line, we say it's nonlinear. So the big ideas here of this page is linear functions have x with an exponent of 1. Any function that has x with an exponent other than 1, or an absolute value of x, you need to say is nonlinear. Nonlinear. And there is one exception which we will get to later in the year, x to the power of 0, which kind of seems funny to think about. Moving on to slope, rate of change. Again, I encourage you to pause the video, copy my notes, and then as we talk through them, make sense of it. Pause, rewind, go back. Part 1's a recap. We've already seen that positive slopes means the function's increasing. The line should be going up. And negative slope means the function is decreasing. The line is going down. So let's see what happens when we change the absolute value of the slope. In other words, what if we really don't care if it's positive or negative, going up or going down? We're going to see what we refer to as the steepness that slope measures. Okay? So in example 3, we have a slope right here of positive 1. And this is because positive one, it's going to have the same rise, the change in y, over the change in x. Up 1 over 1, up 2 over 2, up 3 over 3, up 5 over 5. The rise over the run is exactly the same. Which means this line, we would say in math, has a steepness of 45 degrees. Think of steepness as if you're climbing a mountain, and a mountain is really steep, as opposed to a small hill that you're on. Right, so maybe this is a mountain you're on. That's a very steep mountain, you're afraid to go down it. But if you're on a little hill, it's less steep. Okay, so we're going to refer to slope now as steepness. And we say this is 45 degrees because there's a right angle in your quadrant. And we sort of cut it in half when we make a slope of 1. So half of 90 is 45. Here's a line with a slope of -1. Again, going down. We would also say this is 45 degrees because it's still cutting a 90-degree angle in half. But it's just decreasing. So notice, these two lines, even though one's positive, one's negative, the same steepness. The same steepness. The same slope. One's going up, one's going down. Positive, negative. Now looking at two more lines, you're going to see a slope of 2 and a slope of 5. Notice which one is steeper. Yeah, slope of 5 is steeper. It's much steeper. It's closer to the y-axis. Okay. So it seems like the bigger the number, the steeper the line. The bigger the number, the steeper the line. Let's take a look at the next one though, because now there's two negatives. We have a slope of -3 and a slope of -4.5. And if we're just thinking about which one's bigger, well, -3 is actually bigger than -4.5. However, -4.5 is the steeper line. So this tells us that the greater the absolute value, 5, for -4.5, of the slope, the steeper the line. So when you're asked questions about which line would be steeper, don't focus on positive versus negative, focus on the numbers. 3 versus 4.5. 4.5 is a bigger absolute value, steeper line. And this is because the rate of change of y for every change of x is greater. A couple more. What if we did fractions? M equals 1/2, M equals 1/5. Well, you'll notice these are pretty less steep lines than we've seen before. But again, M equals 1/2 is going to be greater. A greater steepness. Okay. So this is really just saying that you can see that lines with slopes that have an absolute value less than 1, 1/2 is less than 1, 1/5 is less than 1, they're less steep than 1. They're less steep than 45 degrees. Okay. So if I had 3 graphs, 1, 1/2, 1/5, 1 would be the greatest slope. It would be the steepest line. In the last two examples we've seen before in class, lines with a slope of 0 are horizontal, they go side to side. Lines with undefined slopes are vertical. And we just want you to pay attention here to, well, lines with a slope of 0 are parallel to the x-axis, they never hit the x-axis, and they all have the form y equals a number. So if this is hitting the graph at 5, that equation would be y equals 5. Opposite, lines with undefined slopes are vertical. They are parallel to the y-axis. So if this is hitting the graph at 4, we would name this equation x equals 4. X equals a number. And those are the big ideas about slope, is to remember that the greater the slope, the bigger the number of slope, the steeper the line. Lastly, let's see what happens when we change only the y-intercept. We're moving on to our third big idea here. Only the y-intercept. So I have 3 graphs, y equals 1/2 x plus 1, y equals 1/2 x plus 4, y equals 1/2 x minus 3. You'll notice, slope stays the same. which means the steepness does not change. But if you look at my three graphs here, it started at 1, pushed up to 4, and then went all the way down to -3. So when you change only the y-intercept, the function moves up or down. And it's very interesting that when we have lines with the same slopes, this is going to mean that, well, the steepness is the same. But when the different y-intercepts, we create parallel lines. This is very important moving forward. So can we write the equation of a line that is parallel to y equals -2/5 x minus 6? Well, you just need to create an equation that has the same slope but different y-intercept. And I encourage you to pause the video and try these 4 questions. And the only thing you need to remember is, in order to create parallel lines, you need to have 2 equations with the same slope but different y-intercepts. The last thing I want to talk about before showing you the summary page is, let's see what happens when the y-intercept is 0. So all 3 of these graphs have a y-intercept of 0. I don't see a number, plus something, plus something. So if I don't see a number, it's plus 0. And notice that each of these graphs, when they have a y-intercept of 0, they travel through the origin. So the big thing to remember is, if you don't see a y-intercept, that means it starts at the origin. And the last thing I'll kind of leave here to sort of sum over is I just have you go through each of these bullet points and just reread them. Okay? It summarizes everything we talked about today. And again, the goal today, understand the big ideas about linear functions.